Good evening, guys. How's it going? Y'all ready to grab some polynomials? Have you already gotten started? How far into it are you? What homework have you done? Tell me. Tell me what you've done. How's it going? How was your weekend? Are we ready to begin? All that kind of stuff. All that jazz. Yay! Way to be some math. Way to be here. Hey, Thomas. How's it going? You feeling better? 80% better? I don't know how you did it, but my throat hurts now. So somehow or another you gave me strep. Not sure how that happened. Over Discord. Not sure how. Doesn't make sense to me. Hey, Austin. Good. I'm glad you're feeling better, Thomas. I don't understand how viruses work. How they transfer through Discord. None of y'all better get the coronavirus. Now that I know the viruses can go through Discord. I haven't left my house. I can't be sick. It's not possible. So, y'all ready to do some polynomials? Did you look at it at all? Have you done any of the homework? Before I get started, so I know what I'm teaching. I saw a couple of people have turned some stuff in. So a couple of people have been looking. I've had a couple of questions where I've been like, show me your homework and then I'll help you. So, make sure you're doing your homework first. Hey, Rachel. Have y'all done anything, any of it? Have you watched any videos? Am I starting from scratch? Or have you looked at any of it? Tell me, what all am I teaching tonight? Where am I starting? Am I starting at the beginning? Yeah, that's what I thought. Thomas is done with the first two. Austin's not done anything. Great. Perfect. I like the honesty. I know where to begin. Know where to begin. What about you, Rachel? Where are you? Somewhere in the middle? Watch most of the videos except for the last ones. Okay, good. Good, 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 good. Alright, so I can breeze through the first part. Austin will catch it up quickly. And then if y'all do you have any major questions? I kind of go through it, and then y'all ask questions as I go along. Make sure you're understanding everything. This week you're mainly going to have to factor. Yeah. I'm going to try tonight, Thomas, what I'm going to try to cover is end behavior, which you've already done, graphing polynomials, which you've already done, and irrational roots, which you have not done yet. So I'm going to try to cover all three of those all in boom, 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 because Thursdays is possible rational roots, and that's going to take the full hour on Thursday. I mean, that's going to take at least the hour on Thursday. So I'm going to try to do boom, boom, boom. That's why I was like, y'all get ahead so that tonight I can breeze through it. That is a plan. Yay, September. How much of it have you done, September? Have you done it all? First two? Last two? What all have you done? I know you've done some of it. Which of it have you done? Well, September tells me, I'm going to tell you first of all what a polynomial is. So we've dealt with some polynomials. We've graphed quadratics. We've graphed linear. Okay, good, September. We've graphed linear. We've graphed quadratics. We've graphed cubics. We're just going to add to that. So a couple of things that make polynomials polynomials. Polynomials have to have non-negative integer exponents. So let me write that down. Non-negative integer exponents. So those of you who watch the videos, you already know that. In other words, in my exponents here, they've got to be not negative, and then they have to be pretty numbers. In other words, they have to be whole numbers. Okay? That's what this integer means, like whole numbers. But integer means negative and positive. So then we got to put in the not negative. Why? Well, if I had something like 3x to the negative 4, y'all know that that negative 4 means what? What does that negative 4 mean? What does that mean? Show Jimson. Jimson's moderating today. So y'all got to prove to Jimson that you know something. He hadn't been around. Yeah, they know what a negative exponent is. They can tell you what that negative exponent means. They're that smart. Watch. They're going to tell you. They are. I know they are. They're going to jump in here. They're going to show him that they're listening. Number one, that they didn't just walk away and go get like some coffee or something. Yeah, they're there. I know they're right here, and they're going to jump in and tell you. Because that's the kind of class this is. Oh yeah, you're close, September. You're close. Think though, negative. You're thinking this. You're thinking that. That would be the root of 4. Remember, the fractional exponent is the root of 4. Oops, I forgot the x. That's wrong. This is what that is. This is the root of 4. Yeah, never mind, Jimson. Obviously, they don't know. So much for that. They just killed me. September's the only one that's listening, and she's already forgotten from last week. And so now I'm like disappointed. Oh well. Okay. So this is the 4th root of x. The exponent. Oh, yay! Way to be, Austin. That's exactly right. This is x to the 4th on the bottom of the fraction. So it actually looks like that. It was close. You were close. And there's no negative. Notice that the negative goes away completely. Never mind, Mr. Simpson. We'll pretend, okay, that they know something. Normally they're pretty good. I don't know what happened. Okay, so negative exponent there. Fractional exponent there. So notice those guys, this is a rational, and this one's a root. Those are not polynomials. They're making me look bad. I'm going to fail them all just because of their responses right now. Okay, then that's what makes a polynomial a polynomial. Then they also have to be smooth and continuous. In other words, we're not going to have any of this going on. That is not a polynomial because it has discontinuity. So that's no good. Polynomials are smooth and continuous. They're smooth and continuous. So that tells me, since they're continuous, it tells me the domain of all of them is going to be all real numbers because they go from one side to the other. So all real numbers. Then they are smooth. So in other words, no kinks in them. So an absolute value is not a polynomial. It has this sharp turn. It's not a polynomial. So they're nice and smooth and continuous. So the ones we've looked at before are quadratics. Well, they're linears, quadratics. We've looked at the parent of the cubic function. So I'm going to show you a family member of the cubic instead. little more turning. Then, so here's a polynomial. Notice non-negative integer exponents, non-negative integer exponents, non-negative integer exponents. I'm going to do to the fourth power. We have not graphed this one yet, but we're going to this week. This is not the parent, but it's similar. It's a family member. I'm going to show you y equals x to the fifth. No, I'm not. Yeah, I am. There you go. Couple of things I want you to notice about that. Right now they are all rising on the right. They're all rising on the right. Do you see that they're all rising on the right? But do they all rise on the left? I'm here by myself. It's just you and me tonight, Jimson. I can tell. It's just going to be the two of us. I don't know what happened to, Austin and September are here. That's good. They're here. So that's good. So we're looking for patterns. So here I got rising on the right, and then they don't all rise on the left. So what's the pattern for them on the left? What's happening on the left, and what's the pattern? For those of you who've watched the videos, this should be really easy. And for those of you who haven't, then see if you can find the pattern. Oh yeah, always on the right. And then what's happening? Yeah, Austin's always with me. He's here. That's what it is. Thomas is already working on his next homework. There's Rachel. There's Rachel. Oh, okay. She's got lag. Okay. That's good. That's good. All right. I'm just going to tell you. When our exponents are odd, so check out the 1, the 3, and the 5. So when the degree of the polynomial, by the way, we call that highest degree, the largest degree, is called the degree of the polynomial. Mr. Simpson, they were supposed to watch some videos beforehand, so I'm like flying through this part. Degree of the polynomial. The dope is the degree of the polynomial. Perfect, Thomas. And that degree tells me what's happening on the left. So when it is odd, when my degree is odd, I know that I'm going to have the opposite end behavior. Yeah, perfect, perfect, perfect. So that degree tells me what's happening on the left. When the degree of the polynomial is even, such as my 2 and my 4 and my 6, then I'm going to have the same end behavior. You got it. You got it. Good, good, good. Now, right now it's all on the right. It's all rising. But remember when we graphed, sometimes our quadratics turned upside down. Sometimes our linear did like this. Sometimes our cubic flipped. What made them reflect? What made them reflect was that leading coefficient. If we had a negative out front, it reflected it. If we had a negative out front, if I had a negative out front, it reflected it. So, on the right, when I reflect it, when I have a negative out front, it's going to flip it and make it on the right. It's going to make it, that's right. That makes it go down on the right. So when I have a leading coefficient that's negative, it's going to fall to the right. But when my leading coefficient is positive, it's going to rise on the right. All right, there are a couple other things. Also notice the turns. What do you notice about the terms? Tell me the pattern you know because you've either watched the videos or you can see the pattern. What's the pattern you see on the terms? How many turns do I have? So this one has 0 turns. That one has 1 turn. This one has 2 turns. This one has 3 turns. 1, 2, 3, 4 turns. Hey, there's Jacob. Way to be here, Jacob. Good. The degree of the polynomial minus 1 equals the number of terms that we expect. And then one last thing that degree of our polynomial tells us, and that is, if you look and see how many times it crosses the x-axis, assuming it crosses the x-axis nicely like that, those x-intercepts, or the roots, for sure it tells us the number of roots. So notice there are 3 x-intercepts there. It crosses 3 times. Here it crosses 1, 2, 3, 4 times. There it crosses 1, 2, 3, 4, 5 times. So the degree of the polynomial is also going to equal the number of roots. Now, it is true that it doesn't have to be, hey Cherish, it is true that they don't have to have real roots. That sometimes those roots might be imaginary, so there might not be that many x-intercepts, but they are for sure going to be that number of roots. There will for sure be that number of roots. Now in this class though, you know we keep it real. So the number of x-intercepts we have will match the number of roots we have. But just so you know that they don't have to be, like if this quadratic were up there, it still has 2 roots because the degree is 2. It's just that the 2 roots would be imaginary. They would not be real. They'd be complex. They wouldn't be real roots. Anyway, what you need to know is that the degree of the polynomial is equal to the roots. We're going to get there, Rachel. We're going to get to that. That's exactly right. And you're exactly right. Because if it hits here, like for instance, here, let me show you. Let me erase all this and show you. I'll go ahead and talk a little bit about it. You're exactly right. We're going to get to that multiplicity a little better, but I'll show you now this. On our parents, you know that quadratic came down and hit and turned around. So if I think about the x-intercept, it actually only looks like it has 1 x-intercept, right? So, but if I factor this thing to find that x-intercept, you know, the y equals 0 for my x-intercept. So either this x is equal to 0 or, well, x is equal to 0. So I end up with 2 linear factors. Because this is a 2, I end up with 2 linear factors. It just so happens that both x values are equal to 0. So it's 0, 0 happens twice, or we call that a double root. Or you're exactly right, the multiplicity of that root we say is 2. So the multiplicity, this is a double root. Or we say the multiplicity equals 2. Yay, yay, way to be, way to be. Okay, so let me walk you through, now that you know a little bit about polynomials, let's walk through and graph one. And then I'll talk about the pieces as we go through. By the way, I'm super specific in what I want on that end behavior. You're going to have to tell me why it's doing what it's doing. So look at my examples. I'm going to do some examples here. I'm going to point it out to you. Make sure that you're including everything. Good question. I want to know, though, first, what's the leading coefficient? Or what's the degree? Whichever one. You tell me. What is the degree of this polynomial? What's the degree of that polynomial? Hurry, hurry, hurry. Hurry, hurry. They're loading. They have lag. They live in a hole where their internet doesn't quite get to them. Or Thomas is graphing. He's trying to make it look pretty. Oh, Rachel says 3 is the leading coefficient. Because my degree of my polynomial is 7. Good. I tried to trick you by putting it in a different order. So it's out of order. It's not in descending order. So let's put it in descending order. So 7, and then the 5, and then the 3. And you're right. The leading coefficient is 3. And the degree of the polynomial then is 7. There we go. There we go. Now, I want to know this. Here's what I want to know. What do I care about that 3? What's important about the 3? What does that tell me? The 3 tells me something about what's happening with my graph on the right. And what do I care about it? What is it that's important about it? What is this? What's important about this 3? You remember? I know I blew through it really fast over there, but for those of you who've watched the video, and for those of you who've already done the first assignment, you know what's important about this 3. What's important about that 3? Yay! It is positive. That's what we care. This is important. You have to include that because that's what's important about that 3. And because it is positive, it is going to rise on the right. It's going to go up on the right. That's exactly right. But the way you know it rises on the right is the fact that that's positive. So you've got to tell me that. Good job. Now, what do I care about that 7? What's important about this degree? Why is that important? What do I care about it? What does that help me find out? What do I know? What is that 7 going to tell me? So, on the leading coefficient, every time, every one of these polynomials this whole week, you're going to make sure to tell me that it's positive, so that's how you know it rises right. Good. September says, well, I know that it tells me the number of roots. And that is going to tell you the number of roots. And that's going to be important as we find our X-intercepts or our linear factors. But it's also important because it tells me what's happening on the left. Exactly. And the way I know that it's going to be opposite is because it is odd. And you're exactly right. Because it is odd, it's going to do the opposite in behavior. So again, you're telling me how you know what's happening on the left. That one went up. Since this does the opposite, it's going to fall on the left. And then you're right, it tells me it's 7 roots. And then there's one other time. Oh yeah, you told me already. That it is 6 terms. Wow, that's a lot of terms. We expect it to have 6 terms. Okay, so this is really important. On every one of these polynomials you do this week, you're going to start off this way. You're going to tell me the leading coefficient, what it is. If it's positive, then we know it rises right. If it's negative, then we know it falls right. This always is going to be right. And then the degree tells me what's happening on the left. If it's odd, it does the opposite. If it's even, it does the same. then you're right. It tells me the number of roots and then how many turns there are. So we're going to include that every time, and then we're going to go ahead and put a sketch down so we can start to visualize what this thing looks like. You know, what does this polynomial look like? Well, it's going to rise on the right, it's going to fall on the left. I expect 6 turns. 1, 2, 3, 4, 5, 6 turns. Something like that. Whew, that's a lot. Okay, so every polynomial you graph this week, that's how you're going to start this thing. All right, now once we've got that sketch done, then our next step is going to be to find the y-intercept. How do we find the y-intercept of any graph? We've done y-intercepts before. How can we always find the y-intercept? Remember, think about y-intercepts. You know, that means where it's going to intersect this y-axis. You know, where does it intersect that y-axis? So what do I know about the point when it intersects that y-axis? Good! Our x equals 0. That's exactly right. So that's exactly right, guys. You're just going to put in 0 for x. Geniuses. Now, see, Jimson, now they've come alive. You see, they really are. They are here. Just took them a minute to warm up. They were intimidated by you at the beginning, being all shy and stuff, hiding behind me. So good. I'm just going to set all my x values. I'm going to evaluate the function where x is 0. So I'm going to stick in or substitute in 0 for x everywhere I see x. Oops. 0 cubed. By the way, our haiku today is toiling away, spending time on spending time, oh so wastefully. But y'all are not doing that, right? Y'all are not just wasting your time. You're like really spending your time working. I know y'all. Y'all are not wasting time. None of y'all are. Okay, so 0 times 3 is 0. 0 times 39 is 0. 0 times 108 is 0. So in this case, f of 0 equals 0. Now, x-intercepts are points. So we need to write it as a point. In other words, with an x value and a y value. So I'm going to write it as a point. 0, 0 is that point with an x value and a y value. You're exactly right, Cherish. That's what we're going to do next. So next we're going to find our x-intercepts. And our x-intercepts are along here, and you're right, those are y equals 0. So here we're going to plug in y, 0 for y. So instead of writing, remember that y is just the same as f of x, right? I could replace this f of x with y. Those two things are the same thing. So I'm just going to take and put a 0 in for that. And then I'm going to solve. And how do I solve for x? I've got 0 in there for x. How do I solve? Yeah, I agree. A y-intercept and an x-intercept are a point. So when you make it to pre-cal, you got to tell him that y-intercept is 0, 0. It's not just 0, it's 0, 0. That's the point. Yay! We're going to F this thing. F it. Factor it. And remember, when we factor it, the first thing we look for is the greatest common factor. What's my greatest common factor here? Greatest common factor, let's see, does 3 goes into that. Does 3 go into that? Yeah. 1 plus 8 is 9, so 3 goes into that. I think I can get a 3 out of all those. And then the biggest x I can get out is an x cubed. So start with that greatest common factor. Then, what times x cubed would give me x to the 7th? That'd be what? X to the 4th? Because you add the exponents. You got it. You got it. 3 goes into 39, what? 13 times? And then an x squared. And then 3 goes in there 3 times with 1 left over. 3 goes into 18 6 times. So let's make sure 3x cubed times that. Well, you add those exponents, yeah. Here, I'd add the exponents. There, okay, looks good. Am I done factoring it? Am I finished? Remember that this 7 right here tells me that I should have 7 linear factors. In other words, if I wrote them all with the power of 1, I would have 7 of them. They do know how to factor. Don't you want them in your class? I mean, if they just know how to factor, that's enough, right? Oh yeah, we're not done. So you can tell me how to factor this. How do I factor this thing? AC method, yay! So, what is my A? Well, see if you can factor it. I bet you can do it. Your A is 1. Your C is 36. Your AC is 36. Factors of 36 that add up to be 13 or negative 13, actually. Negative 13. Oh, that's right. We are going to be able to go straight to the shortcut because our A is 1. Now, it is a little tricky, but we can still cut to the chase because our A is 1. So what are those factors going to be? Let's see, 1 and 36, no. 2 and 18, no. 3 and 12, no. 4 and 9, 5, 6 and 6. I think I've got them all. I like 4 and 9, but they both need to be negative in order to get to that negative. Yeah, there you go. Negative 36. You got it? Now, September's right. We can skip straight to the punchline, but we're going to have to be careful right here because I need these two to multiply to be x to the 4th. So normally we just put an x and an x when it's x squared, but here, because it needs to multiply to be x to the 4th, this is an x squared, and that's an x squared. Am I done? Do I have it factored completely? Is it completely factored? Yes? No? Am I finished? I'm all done? I can start graphing it now? What now? Oh, look at that! You're right. This is a difference of squares. And this too is a difference of squares. So I can keep factoring even more. Plus, it's not down to its linear terms. In other words, I want this to be down to 1. We're going to factor these guys until we get it down to our linear terms. And we should have 7 of them in the end. But you're right, this is a difference of squares. So 3x cubed, x minus 2, x plus 2. Over here, x minus 3, x plus 3. Notice, since I'm solving for x and I have this equal sign with a 0, I can divide both sides by 3. Divide this side by 3, and you get 0. Divide that side by 3, and that 3 divided by 3 is just 1. So you can get rid of your 3 because it's an equal sign. You can divide both sides by 3. I'm going to write this as linear factors in that I'm going to make this x, I'm going to write it as x, x, x. It's a triple x there. And then we have it now factored. We had it completely factored there. But I want to solve it for x-intercepts. By the way, notice I'm down to 7. 1, 2, 3, 4, 5, 6, 7. I want to make it x-intercepts though. And remember, that's exactly right, September. I've got to set each one of them equal to 0 and solve to find those x-intercepts. So I've got x equals 0, or x equals 0, or x equals 0, or x minus 2 equals 0, or x plus 2 equals 0. I'm not doing a very good job of using the board tonight. X minus 3 equals 0, and x plus 3 equals 0. So I should end up with 7 x-intercepts, 7 roots. So there are each of my factors. Now, this one is a 0. Remember, my y value was 0, so the x-intercept there was 0, 0. The x-intercept here is 0, 0. The x-intercept there is 0, 0. The x-intercept there, add 2 to both sides and you get 2, 0. Subtract 2 from both sides and you get negative 2, 0. Add 3 to both sides and you get 3, 0. Subtract 3 from both sides and you get negative 3, 0. Now, oops, I'm going to need that in a minute. I just erased it. Oh well. So now notice that this one shows up 3 times. The multiplicity of this root is 3. So that multiplicity just means how many times do we see that root? How many times does it show up? So in this case, 0, 0 has a multiplicity of 3. 2, 0 only shows up 1 time. So it has a multiplicity of 1. Negative 2, 0 only shows up 1 time. It has a multiplicity of 1. 3, 0 only shows up 1 time. It has a multiplicity of 1. And negative 3, 0 only shows up 1 time. It too has a multiplicity of 1. Now, the multiplicity is important because it tells us what's happening in the middle of our graph. So we looked at the ends, but this multiplicity tells us kind of what's happening in the middle. At each one of those points, what's happening. When the multiplicity is even, at the point it's going to turn around. So you remember this thing right here? one showed up twice and had a multiplicity of 2. 2 is even, and it turned around at that point. It hit that point and it turned back around. So when the multiplicity is even, it bounces or turns at the point. When the multiplicity is odd, so think about our cubic function, you know, this parent cubic function, that's x cubed. Well, it shows up 3 times, 1, 2, 3. Notice it crosses at that point. So when I have an odd multiplicity, it's going to cross at the point. So these are all odd. So it's going to cross at all of these points. This one's odd. That one's odd. You're odd. You're odd. I'm odd. And so it's going to cross at all of those. So an odd multiplicity means it's going to cross or pass through at that point. An even multiplicity means it's going to turn around at that point. Oh, there's Cheyenne. Woohoo! Okay, so pieces we're going to graph. The y-intercept was 0, 0. Our x-intercepts are over there. And then we know it looks something like that. I'm going to erase all this and graph it now. My use of board on this has been awful. Oh well. Sometimes we have an off night. I'm going too fast, that's why. I want to get through a lot tonight. Plus, you've already seen the videos. So, 0, 0. My y-intercept. 0, 0 shows up 3 times. Notice I am not counting this guy as a 4th one. The y-intercept, even though it also is a y-intercept, he doesn't count as a 4th root for my multiplicity. My multiplicity is just how many times it shows up as an x-intercept. So it only showed up 3 times for the x-intercept. So don't count it as the y also. Does that make sense when you're talking multiplicity? All right, so I know that at that point it's going to cross, but I'll get back to that. I know at 2, 0, there's a point. I know at negative 2, 0, there's a point. I know at 3, 0, there's a point. And I know at negative 3, 0, there's a point. Okay, once I get my points on there, then I'm going to go back to my end of behavior and look. I know on the right, it's going to rise. So from this point, it's going to rise up. I know from this point, it's going to fall. So from my last point, it's going to fall. Then the multiplicity tells me what's happening on each one. Because they're all odd, it's going to cross through. So it's going to, at this point, come up. Now, how far up it goes, I don't really know. I don't know if it goes way, maybe it looks like this. And it comes way up here before it turns around. Or maybe it's super flat and it comes like this. And then it just barely goes up and it turns around. We could find out a little bit more by plugging in an x value, like negative 2.5, and finding out that y value. But you don't have to go through that for me. If you have the x values and the the x-intercepts and the y-intercepts and the multiplicity and the end behavior, I'm going to be happy. In calculus, we learn those turnaround points. So we really can't find it out unless we just we get lucky. In calculus, we find those turnaround points. So, just make it look pretty in here. It crosses through, and somewhere it's got to turn back around to hit that x-intercept. Then, once it hits this x-intercept, we know it's going to cross again. And again, I don't know how far down it goes. In calculus, we'll find that turnaround point. So, somewhere, make it look pretty. Turn it back around. Then it's got to hit that point. I know it's going to cross through there because it says the multiplicity was odd. So it crosses through there. Then somewhere it turns around because it's got to come through that x-intercept. And again, I know it's going to cross because the multiplicity was odd. And then one last time, it's got to turn back around. That's right, we do this all over again. You just learn the turnaround points. Now I know this goes forever and ever, so I put an arrow on it. Now maybe it doesn't quite look like mine because this one, my sketch, had more turns. So, if you want to make it look, well, I want it to have 2 more turns. Well, you could do something like this where it goes 1, 2 more turns. There you go. Now it's got all the turns in it. But this is good enough for me. Then label your points. Be sure to label. Those are x-intercepts, x-intercepts, 0, 0 is an x-intercept, and a y-intercept. 2, 0 is an x-intercept, 3, 0 is an x-intercept. There we go, we've graphed that. All right, let's do another one. Not always, Rachel. It won't actually. When we talk about rational functions, a lot of times I do even and odd, and it lets us know if they mirror each other or not. But it's not always necessary. It's not necessarily that they will. If I talked about even and odd, we could maybe see that more, but not here. What we do know is they're nice and smooth and continuous. So don't do something like this on your graph. Don't do something crazy where they go, Geek. Don't do that. No, it's nice and smooth and continuous and pretty. Make them nice and pretty. But it's not necessarily that they'll be symmetric here. So, like he said. All right, let me do another one. Maybe I'll use the board better. All right, I'm going to do this one right here. Let's do... let's skip to this one. Let's do that one. Okay, every single time we're going to start with our end behavior. So, what do you see first? You should already be telling me, what am I going to do first? What do I notice first? What do I have there first? Yay! Good. So the first thing I'm going to do is rearrange this because I've obviously got it out of order again. Keep trying to trick you. And you're right. Our leading coefficient is -1. What do I care about that -1? What's important with that? Yay! That's a negative. And because it's our negative, that's exactly right. That's what we're noticing. Because it's a negative, it's going to first fall on the, this always tells me about the right. But you're right, it's going to fall on the right. Then I'm going to look at that, you know, I'm a Simpson, so a degree of a polynomial is clearly a yeah, that tells me it falls on the right. Then the degree of the polynomial is 2. What do I care about that 2? What's important about that 2 is the fact that it is even. And so I know that it is going to be the same on the left. Good, 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 good. So here it falls right, so I know on the left. Hi, Dad. Come on in. I know on the left, it too is going to, if it falls on the right, I know it's going to have the same in behavior, so I know it's going to fall on the right. I mean on the left. You can move that and just walk on through. That's all right, you're fine. Yeah, I have. Come on in. Come say hi to my class, Dad.
From here?
No, from over here. Come over here. Look, my dad came and joined us. Say hi, Dad.
Hello.
See, they're here. They're commenting.
I see.
So they can comment and tell me. Johnny says hi, Dad.
Oh, hey, Johnny.
And there's all my students. They're like, hi, Lead Simpson.
Hello, hello.
All right, so our degree of our polynomial is 2. What else does that degree tell me? It's Dad. You didn't see him, Cheyenne? I get him back up here. Come look again. Come up here again. Make him get up here again. Do I look like him? I look like him? Look like just like my dad? Maybe not. Maybe I look just like my mom. Maybe Johnny looks more like, he is cute, isn't he? He's so cute. All right, so the degree of the polynomial is 2, and that tells me that I have 2 roots, or 2 linear factors, or 2 x-intercepts in this case. And then the degree of the polynomial is 2. So I know that it just is going to turn one time. Look, it's just a quadratic, guys. The degree of the polynomial is 2. So this is just a quadratic. We've graphed quadratics before, right? We know what a quadratic looks like. We know it's that parabola. It's like this, or maybe it's like this. Well, since it falls on the right and it falls on the left, it looks like that. Don't we know what a parabola looks like already? This is just not in that normal form that we look like. You know, it's not in the transformational form that we usually see it in. This is in its standard form. But we know it's going to look like that. It's still being reflected. There's that quadratic. All right, so step 1, every time in behavior, be sure to tell me those important pieces. What's happening on the right, what's happening on the left, and how you know. Be sure to include that in there. Okay, next we're going to find the y-intercept. How do I find the y-intercept? How do I find that y-intercept? Yeah, with my x equal to 0. So just substitute that x in for 0. Everywhere I see an x, I'm going to substitute in 0. and I solve. So what is my y-intercept? What is my y-intercept? Tell me what it is. Tell Mr. Simpson, what is the y-intercept? What is it? What is the y-intercept? Don't you just answer 5. It's not just 5. That y-intercept is a point. It's a point. So be sure and tell him the x value and the y value. Your y-intercept is 0, 5. That's what the y-intercept is. Good, Rachel. Good job. Yay. Oh, you're close, September, but flop them, because your x value is 0 and your y value is 5. So you've kind of got it written down to help you remember which is which. Woot woot! Way to be, Rachel, way to be. All right, now the next, we found our end behavior. We've done our y-intercept. The next piece that we're going to do on every polynomial is the x-intercepts. How do we find the x-intercepts? X-intercepts. How do we find those x-intercepts? Yeah, with y equals 0. So this time I'm going to take and plug in 0 for y, or substitute in 0 for y. And you are exactly right, Thomas. Once I've substituted in 0 for y, I'm going to F it. I'm going to factor it. That's exactly right. F that thing. Let's factor it. So now, what's the first part of factoring? What do we have to do first with factoring? A GCF, which in this case is a negative. Anytime you have a leading negative, you have to factor out that leading negative. Factor out that -1 every time. So -1 comes out. Anytime there's a leading negative, factor out that leading negative. That's got to go. Get rid of it. Yes. Yes. 0 squared is just 0. 0 times 4 is 0, so it leaves me with that 5. Yeah, I didn't explain that, did I, Cheyenne? So that's just 0. This is just 0, so it just adds up. It just leaves us with that 5. Over here, now I'm going to factor it. My A is 1. My C is a -5, so my AC is a -5. Factors of -5 that add up to be +4. Factors of -5 that add up to be +4 are what? 1 and 5. To be a +4, I need that to be positive and that one to be negative. Yay! Then, because my A is 1, I can cut straight to the chase. Let's go straight to the punchline here. So I got x minus 1, x plus 5. I'm also going to do this. See that -1? I'm going to get rid of it because it has a equal sign with a 0. So I'm going to divide both sides by a -1. I can only do that because it's an equation. I can divide both sides by -1. Notice that I have 2 factors, just like we said we were going to have. And you're exactly right, September. X equals 1 because you set that equal to 0 and solve, or x equals a -5 because you set that equal to 0 and solve. Now, what are the X-intercepts? Tell Mr. Simpson what the X-intercepts are. That's right, eliminate that -1. I haven't seen that show, so I don't know who Carol Baskin is, but I know that there's some sort of going on. And that's what we did to that -1. Whatever Carol Baskin did to her husband or something. I don't really know. I haven't watched the show yet. Y'all tell me. Yay! They wrote them as points. So my X value and my Y value. My X value and my Y value. Okay, now, on any other polynomial, we would start to graph it. We'd do the end behavior, the Y-intercept, then the X-intercept, and then we graph it. But on quadratics, we can actually find that turnaround point. Remember on the last one, I was like, we can't find the turnaround point. I don't know where it is. We'll have to wait for calculus. But on quadratics, we can find the turnaround point. So we're going to find the turnaround point. So let's look at this quadratic for a minute. Quadratics are symmetric. So, you know, they are symmetric. All quadratics are symmetric. So there's this line that goes through the middle of them that we call the axis of symmetry. This is called the axis of symmetry. So remember when you were in kindergarten and they gave you the butterfly and then you got to do the paint dollops on it? Y'all remember that, right? We've done this before, I think, in this class, where we got to do some paint dollops. And then you folded it on your butterfly, and when you did, it folded over, and it was so beautiful on the other side too, where the paint went on the other side. So in kindergarten, you were learning about symmetry. You remember doing that project? Now's the time of year to do it, right now. So those of you with kids at home, y'all teach them about symmetry. Get out, you know, make your little butterflies and do some paint. Show them about symmetry now. We're going to find the axis of symmetry for all of our quadratics, otherwise known as the AOS. And the way we're going to find that, it's going to sound a little bit familiar to you because it's x equals -b all over 2a. That sounds familiar, right? A little bit? If this is on the x-axis, then every x is the same, and the y is just the inverse. I don't understand the question. Jimson, do you understand the question? Maybe you understand the question better. Sometimes I don't quite get it. Maybe Jimson will understand. This is how I'm going to find my axis of symmetry. I'm going to find this vertical line where we can fold it and both sides match. Now, it's a vertical line. So when we describe that vertical line, we have to put x equals some number. So when you get ready to label this thing, you're going to label it as x equals some number. That's how I feel too, Jimson. I didn't quite understand it. Maybe September can explain. Okay, so I'm just going to fill in. So my A we already said was 1. Actually, we better go back to the beginning. What is my A? My A is actually a -1 because here, the reason it became a 1 was because we factored out that -1. That was important for solving. But here my A is actually a -1 when I get ready to look for that axis of symmetry. Yay, that's right, Austin. It comes from the quadratic formula. And in pre-cal, Jimson will show you why this works. He does some fancy verification and such, where he shows you how we complete the square and moving the quadratic formula around. It's some cool stuff. But in this class, I'm just going to tell you, trust me, this is how we get it. So our A is -1, and our B here, back to the original, is a -4. I just plug it in. So x equals a negative of that -4. And on bottom, 2 times my A is a -1. That's right, we get to do this all again. Once you know it in college algebra, pre-calc, it's so easy. Because you've already done it in college algebra. And then calculus, it's just the same stuff again. It just keeps building and building and building. So you take Jimson for pre-cal. And then you can take Jimson again for calculus, or maybe Rimson just for exposure to all the Simpsons. Okay, a negative and a negative makes that a +4. And then 2 times a -1 makes that a -2. So my axis of symmetry is going to be x equals a -2. In other words, there's going to be a vertical line where x equals -2. And on that vertical line is going to be the symmetry. If I fold it on there, then both sides of my quadratic will match. Now notice that the turning point that we call a vertex is on that line. See how the vertex is on that line? So when we find our axis of symmetry, we now know the x value of the vertex. But the vertex is a point. So what I'm going to do is take that x and plug it in to get my y back out. So I'm now going to find the vertex. And the way I find the vertex is I just take this x value of my axis of symmetry, this thing, that -2, and substitute it in. So I'm going to write down fancy stuff that just says that. The vertex is going to be -b over 2a. That's how we found this. And then I'm going to substitute that in. I'm going to evaluate the function there. So that's all that fancy talk says. Just take this and plug it in. So let's plug it in. Plug it in, plug it in. -2, back to my original, plug it in -2. So negative of a -2 squared minus 4 times a -2 plus a 5. So -2 squared is 4. See this negative outside? This is 4, but that negative comes down with it. Shh. A negative times a negative makes that a +a plus 5. Add all that together. Well, that's 4 plus 5 is 9. So the vertex of this is at -2, 9. Notice it's a point, an x value and a y value when we're talking about the vertex. So anytime we have a quadratic, it means more work because we can find the turning point of that. We can find the turning point of that. Okie dokie. So, let me show you the graph. I keep erasing it before I need to. Oh well. Okay, here's the graph. And then we're going to talk irrational roots and be done for the night. Okay, so 0, 5. 1, 2, 3, 4, 5 was our y-intercept. My axis of symmetry was at x equals -2. 1, 2. equals -2. It kind of looks like that asymptote, right? But the asymptote is where it doesn't quite, it gets close to it without ever reaching it. This x equals -2 is just the line that we could fold it on. It's not really part of the graph. It's just there to let us know that's where we could fold it. That's where our symmetry is going to be. And then our x-intercepts are at 1, 0, and -5. So 2, 3, 4, 5, 0. Notice there really is symmetry. If I fold this here, it'll end up there. It's over 1, 2, 3 spots, and it's over 1, 2, 3 spots. So there really is symmetry there. My vertex is on this line at 9. Oh my God, I didn't make my thing big enough. 5. Miss Simpson. In too big a hurry tonight. Try again. 1, 2, 3, 4, 5. 1, 1, 2, 3, 4, 5. Dotted line. 9, 5, 6, 7, 8, 9. Okay, one more thing we're going to do on this quadratic, and that is we're going to find an additional point. We can always find an additional point just by plugging in an x value and getting out a y value. That's always true. We can always find an x value, an additional point that way. But because this thing has symmetry, we know this point right here has a buddy. Your y-intercept is always going to have a buddy or a symmetric point. On the other side, if I fold this on that paper, he's going to show up on the other side. So it's going to have that same y value, and it's going to be double your axis of symmetry. This is 2 away, so his buddy is over here at 4 away. There is my quadratic function. Notice that my vertex up here is at its maximum point. It's up at the highest point. We call that a maximum. When it's down at the bottom, that vertex then is called the minimum. So it's going to either be at the top or at the bottom. But because we fall to the right and we fall to the left, this one is the maximum point. And there we have all of our pieces. Label them all. There's our additional point or symmetric point, our x-intercepts. There you go. What do you think? Not too bad? All right, a couple more things I'm going to tell you. Next thing is irrational roots. So I'm going to slow down a little bit. Because this part, you've already watched the videos for. Some of you have already done the homework for. Y'all are good with this, right? I went through that really, really, really fast. But now I'm going to slow down a little bit for this irrational root part. So let's talk some irrational roots. And you already know some of this. We've already dealt with some of it. For instance, let's see once again if you can impress Mr. Simpson, all right? This is all about impressing Jimson. See if you can do it. About how much is the square root of 11? About how much is that equal to? Okay, so maybe women are irrational. That could be true. But so are men. Tell him, about how much is the square root of 11? You know this. Oh, look, Thomas already did it. He said it's about 3 and a little bit. We know it's 3.3-ish. We know that because we know the square root of 9 is equal to 3. And we know that good guys, you got it. We know that 16 is the square root of 16 is equal to 4. So we know that that square root of 11 is somewhere in between there. And you know it's closer to 9 than it is to 16. So it's about, 3.2, 3.3, somewhere right in there. I'll split the difference between y'all. Okay, so we're going to graph roots that look like this. In other words, we may end up with an x-intercept that looks something like this, the square root of 11, 0. Don't freak out, because you know about how much that is. So when I get ready to graph that thing, here's my x-intercept, my x-axis. I'm just going to say, well, it's over 1, 2, 3, and a little bit. There's that root at the square root of 11, 0. You know, it's just over 3 and a little bit. So don't freak out about it. Don't freak out about it. You can do it. Yeah, it's not too bad. It's okay. Look, Thomas is already done. That's what he's been doing instead of, I don't know, he's been commenting also. Even while he's commenting, he's been doing it. Okay, so you're going to see things that look like this. Let me show you something else. It's pretty impressive, Thomas, pretty impressive. By the way, Thomas, I found out today that if our stats class makes, this is how we're going to be doing it this summer, because it's going to be online. So just FYI, they told us today that all summer classes will be online classes. So we'll get to do some more of this, assuming it makes. I don't know. Right now there's only 4 kids in the class, so we need a few more people to join in order for it to make. Okay, then I'm going to show you something else. It will be fun. It's going to be fun. It's going to be great. The rest of y'all should come take the stats class with Thomas. It'll be so much fun. We're going to do it this way. It'll be great. Now's the time to take stats this summer. Sign up. All right. So back to what we were doing. Let me show you. I always get people complaining on Facebook because their kids will have a number line and they're supposed to help them add and subtract on the number line. And they're always whining about it. Why do they teach my kids this way? It's always funny because they complain about it. Why are my kids learning it this way? Why can't they just add like we did? And then 2 posts later, they'll be like, I'm no good at math. I don't understand math. I'm like, okay, well, maybe we should teach it a different way than what you learned it if, come on. So one of the things I see all the time, though, is this whole number line where we're adding like this, 5 plus 2. So how do we use this number line? That's right, why? How do we use that number line to add? Well, we start at this number, 5. Then this tells us how to go to the right. That plus tells me I'm going to go to the right. And I'm going to go to the right 2 spots. 1 spot, 2 spots. So I added 2, so I was at 5, 6, 7. So look, 5 plus 2 equals 7. So this strategy is going to help us when we're graphing these irrational roots. Because you're going to get roots that look like this, but you're also going to get roots that look like this. 2 plus the square root of 11, 0. So your x-intercept might look like that. Don't freak out. You can graph it because we just use that same strategy. Start at 2, and then you know that 11, the square root of 11, is about 3 and a little bit. So from that spot, you're just going to go over 1, 2, 3, and a little bit. And that's where you end up. So here's that point, 2 plus the square root of 11, comma 0. Also, when we subtract, so if I did 5 minus 2, when they're teaching your kids on a number line, you start at 5 and you go to the left 2. That minus tells you to go to the left 2. So I start here and I go 1, 2 to the left. So 4, 3. We're going to use that same strategy. I'm going to graph the point 2 minus the square root of 11, comma 0. So again, I'm starting at that 2. I'm going to go to the left 3 and a little bit. So start at that 2, go over 1, 2, 3, and a little bit. So there's my 2 minus the square root of 11, comma 0. So if these are my x-intercepts, I start at that 2 and I go one direction and I go the other direction. So this is how we're going to graph those irrational roots. All right, a couple other little things. And then we'll do one with irrational roots and call it a night. So you know how to factor this. In fact, you did that earlier. How does that factor? What does that look like? You know how to factor that. You did it earlier. We missed one direction. Yeah. One direction. One direction. You mean the group one direction? All right. This is a difference of squares, right? So I know that it's x, it's going to be minus and plus, square root of that, square root of that. What about this? We didn't really get to do, I always do this thing with one direction when we're doing matrices. Well, we lost a week out of this semester, so we never got to do matrices. But in matrices, you want to definitely listen to some one direction as you go along and do it. Right, Mr. Jimson? Good. We're going to use that same difference of squares on this. And I know you're like, but Miss Simpson, 11's not a perfect square. Well, how can we use the difference of squares? It's the exact same thing. Exactly the same, where we go 2 parentheses, a minus and a plus, square root of x squared is x, square root of 11 is just the square root of 11. So even when it's not a perfect square, we can still use the difference of squares to factor it. Because this square root of 11 times that square root of 11 is still going to equal to 11. And by putting the signs different, we're still going to end up with 0x in the middle. So you can still just take the square root of whatever that number is when I have 2 terms and a difference in the middle. So we're going to use this strategy when we're finding x-intercepts as well. And then we just solve and graph those. All right, so I'm going to do one with irrational roots, and then we're going to call it a night. Well, no, we're not. We're all going to get on Discord and do our homework. Except for Thomas, who's already done his work. Thomas is going to go play, I don't know, League. What are you going to play, Thomas? You just going to go to bed and rest after giving me strep throat? What's up with that? All right, Dad, I'm going to look behind you. Read off that top one to me. This one right here. Read. this right here to me.
Well, do I have to say what f is?
F of x, and yeah, tell me what those are. It says x to the...
It equals to negative 10 x squared
Okay, cool.
plus x 4 x 25.
Plus 25, like 25x, like that?
No, it's the x was in front of it, I think.
Oh, no, that's good. No x on it. No x on it.
Oh.
No x on it. Okay, so we're going to do this one now. Okay. What game is that? CSGO? Oh, okay. Yeah. But never mind. I'm back. Okay, here we go. Okay, so we're going to graph this one. How do I start? First thing, you guys got this. How do I start? On every polynomial, what are we going to start with? What am I starting with? Yeah, the end behavior. Maybe we first rewrite it to help me out. I sure have had a lot of those tonight where I've had to rewrite. So make sure that you rewrite it if they're out of order. Maybe on the homework I had a bunch of those too. Where do I begin? What do I do? Yeah, in behavior. So I'm looking at that leading coefficient, which is 1. I'm looking at my dope, which is 4. Nope. What do I care about that 1? What's important about that 1? That 1 needs to be, or tells me, it's positive. So it tells me that on the right, it's going to rise since it's positive. Then, what do I care about that 4? You got this. Good job. Way to be, Rachel. What about that 4? What do I care about that 4? I care that it's even. And so we're going to have the same end behavior on the left. So since it was rising on the right, it's going to rise on the left. So I know that the end behaviors are going to be the same. Then that 4 tells me that there are going to be 4 roots. And that 4 tells me to expect 3 terms. You got it. Good job. So now we can sketch it. Rise is right. Rise is left. 3 terms. 1, 2, 3 terms. We got this. Y'all got this. Next, now that we've done the end behavior, what are we going to look for every single time? What are we going to look for? Our y-intercept. And the way we find that y-intercept is x equals 0. So I'm just going to substitute that 0 in. I'm going to evaluate the function where x is 0. Put it in everywhere I see an x. Oh, just here and there, but no x there. So 0 to the 4th minus 10. Oh, well, that's 0 times 10 is 0, so I'm just left with 25. That's 0, that's 0, that's 25. So my y-intercept is a point. It's a point. So it's at 0, 25 is the point. Good job. Y'all are so good. It's just that 25, because that's 0, it just leaves me with the 25. Once I have my y-intercept and my end behavior, now I'm just going to find my x-intercepts. Good job. And how do I find those x-intercepts? Way to be on top of it, Rachel. How do I find that x-intercept? Oh, yeah, it's just y equals 0. So I'm going to take my y and plug it in, because this is just a fancy way to write y. I'm just going to write 0 there for that y. And then we do our favorite thing. We F it. F that polynomial. Factoring. Factor, factor, factor. Yay! Y'all are on fire tonight. Well, Rachel is anyway. The rest of y'all are kind of there. And Austin just quiet tonight. Austin, you okay? Did Thomas give you strep throat too? Because you've been super, super quiet tonight. What's up with that? Usually Austin's my talkative one. He's so quiet. He must be having that strep throat that Thomas had. Spread it around, Thomas. I don't know how you're doing it through Discord, but you are. All right, back to that. So my A is 1. My C is 25. Yay! There's Cheyenne. She's here too. Woot woot. All right, so my A is 1, so I can skip straight to that punchline. I'm going to end up with a, what, a 5 and a 5, but both of them negative. Yeah, good. So negative 5 and negative 5. Now I have to be careful again here, because this is a 4. So I need to make sure that this times that gives me an x to the 4th power. So this is going to be x squared, and that one's going to be x squared. And they were both negative, because a negative times a negative gave me that positive, and a negative 5 plus a negative 5 gave me that negative 10. Oh, I'm not down to linear factors. Remember, I need 4 linear factors. So I'm going to factor this again with a, it's a difference of, well, we're going to make it a difference of squares. So that I have a plus and a minus. And this one also we're going to make a difference of squares. A plus and a minus. The square root of x squared is x. The square root of x squared is x. I think that happens a lot. The lag is bad. I don't know if it's my end. It may be mine, since all of y'all are having that trouble. Then the square root of 5, since it's not pretty, I'm going to write it as the square root of 5. That explains why y'all have been so quiet tonight. Plus, I have been moving fast. Then, each one of them set equal to 0. So now, x is equal to a negative square root of 5. Because you solve, subtract square root of 5 from both sides, add square root of 5 to both sides, subtract square root of 5 from both sides, add square root of 5 to both sides. I have my 4 roots here. Write them as X-intercepts, so they have to be written as points. So So negative square root of 5 comma 0. Positive square root of 5 comma 0. Negative square root of 5 comma 0. Positive square root of 5 comma 0. I don't have to worry about the axis of symmetry. I don't have to worry about the vertex because this is not a quadratic. By the way, sometimes when it's a quadratic, to solve for your x-intercepts, you may have to use the quadratic formula. So at the end, I'll remind you of that quadratic formula so that you can remember. I think y'all know it, but just in case, we'll remind ourselves of what the quadratic formula is. Then let's talk multiplicity. Tell me about the multiplicity of this negative square root of 5, 0. How many times does that show up? Notice he's here and he's there. So maybe I could even write him like this. So he shows up 2 times. The multiplicity of that x-intercept is 2. The multiplicity of this x-intercept is 2. Okay, now here's the tricky part. Do you remember? What does that multiplicity mean? What do I care about that 2? What's important about that? What does that help me determine? That 2, what do I care? Kind of like back here. Do I care that it's even? Do I care that it's positive? What is it that I care about it? Yeah, who cares about 2? Who cares? What we care is the fact that it's even. The evenness of that multiplicity, the fact that it shows up twice, the fact that that's an even number of times tells me it's going to turn around or bounce at that point. So in both of these cases, it's going to hit the point and turn around. It's going to hit the point and turn around. So that multiplicity lets me know what's happening at that point. It's either going to turn, or if it's an odd multiplicity, it crosses at that point. Good, good, good. Y'all got it. All right, let's graph it now that we have all that. I'm going to erase not my sketch, but the rest of it, so I can graph it. All right. There's a point at 0, 25. Man, that's way up there. Let's count by 5s maybe. 5, 10, 15, 20, 25. Then, where is this? Where am I supposed to put a point for the square root of 5? About how much is that? Square root of 5. How's that going to be? You're right, that multiplicity tells me about the middle stuff. That's exactly right, Austin. It tells me in the middle what's happening. So square root of 5 is about, well, let's see, the square root of 4 is 2, and the square root of 9 is 3. So the square root of 5 is in between those two. Closer to 4 than it is to 9. So it's about 2.2-ish. I don't know, something like that. So when I get ready to graph this, I'm going to go over 2 in a little bit. Go over 2 and a little bit. go over 2 and a little bit. So now I'm just going to use my end behavior and this multiplicity to help me. Perfect, perfect. Y'all are good at this. Okay, so on the right, I'm going to rise. On the left, I'm going to rise. I know at this point, it's going to turn at that point. Oh, thank you, Mr. Simpson. You're right. Those are negatives. It's going to turn at the point. So it hits this point and it turns around, which makes sense because it's got to get up there to that y-intercept. So it hits that point, it turns around, it gets up here, it turns around somewhere. We don't know exactly where that turning point is, but that looks like a good place to turn. Then it's got to come back down here. So it comes back down, it hits it, and then we know that it's going to turn at that point. Then we label square root of 5 comma 0 is my x-intercept. Negative square root of 5 comma 0 is my x-intercept. 0, 25 is my y-intercept. And my guys better be using graph paper, Jimson, so that it's nice and pretty. And yes, it needs to be nice and labeled and smooth and continuous, no weird stuff. In other words, don't make it come down and do this. If it comes down and hits like that, it's no longer a polynomial. It's got to be smooth and continuous. So make it nice and smooth. Make it pretty. When you're turning it into me, make it pretty. Gorgeousness. Do it on a scratch piece of paper and then give me neat work. Nothing, no kinkiness. No kinkiness. All right, that's actually 3 lectures. We did 3 lectures tonight. We did end behavior, which you're going to do on every one of them. Oh, I erased it. And be sure to tell me what's important on all of them. We did graphing polynomials. And we did irrational roots. So you now have 3 homeworks you can do. On Thursday, I'm going to look at the possible rational roots. I'm kind of hoping you'll have looked for it beforehand because it is pretty tricky. We get to make a magic hat on Thursday. And then this week you are making a video for me. YouTube stars yourself. All right. Anything else? All right. I'll see you on Discord. And y'all take some vitamin C. Stay home. Don't go partying. Stay home. Trust me on this. All right. And Math Made Simple at Simpson Math. Thanks for watching. I'll see you on Discord. Come join me.